Hello everyone. In the previous lectures we were looking at state space models, we were introduced to them. So, we looked at the standard form of the state space model as x of t is equals to a times x of t plus b times u of t, and output y of t is equals to c times x of t plus d times u of t. So, here x of x is the state vector and u is the input vector, y is the output vector, and A is the dynamics matrix, B is the input matrix, C is the output matrix, and D is the feed forward matrix. So, these are the standard names for these matrices, and so there are two things that we can do. So, given a state space model, we can go back to the transfer function model, and given a transfer function, we can go to the state space model. So, earlier we looked at how can we go from the state space model to the transfer function model using this formula. So, y of s by u of s is c times s I minus a whole inverse into b plus d. So, given a state space model with the matrices A, B, C and D, this is how you can transform it into a transfer function, and this transformation is unique. So, any state space model given, you can only determine one transfer function. So, that is the case of going from state space to transfer function. Now, what about the other way? So, when we go from transfer function to state space, the transformation is not unique. So, that means when you are given one state space model, you can find out multiple transfer function models. So, instead of finding some kind of random some random state space model, we will try to find out some standardized state space models which we call canonical forms. And so, today we will discuss about three canonical forms. First one is controllable canonical form. The second one is the observable canonical form. And the third one is the diagonal canonical form. So, while we discuss about each of these forms, we will see why these names come. So, first one will be the controllable canonical form. So, to derive this, we will start with a strictly proper transfer function on this form. So, this is a strictly proper transfer function because the numerator has a degree of n minus 1 and the denominator has a degree of n, that is the number of poles are greater than the number of zeros. So, what happens in this transfer function is t is equals to 0. Okay. So, when we are given this transfer function, how do you find out a controllable canonical form of the state space model? So, in case you have a transfer function which is not strictly proper, something like you can have here say b naught s power n. So, in that case what you can do is you can simply perform polynomial division and take this b naught out, so that it will come something like this, and rest again remains in the same form. We can again apply the same transformation that we are doing now. So, for now we will stick to a strictly proper transfer function and go ahead with it. So, given this strictly proper transfer function, how do we convert it into a controllable canonical form? So, what we will do is we will deal with the numerator and the denominator separately. So, for that I will take this as y of s by u of s is equals to, I will introduce a new polynomial called z of s. So, y of s by u of s can be written as z of s by u of s times y of s by z of s. So, I am just multiplying and dividing by a new polynomial z of s, and this will be taken as the denominator part, and this part will be the numerator. So, I will just write it down. So, z of s by u of s will just be 1 by s power n plus a1 s power n minus 1 plus so on up to a n. So, that will be z of s by u of s, and then y of s by z of s will be just the numerator. So, these are not any transfer function, we are just introducing them and what do you say, dividing them into two parts just for the sake of calculation convenience. So, now first we will take the first part and we will do some algebraic manipulations as follows. So, I can take z of s times, I can do cross multiplication on this, and then I will get s power n plus a1 s power n minus 1 plus so on up to a n will be u of s. So, now what I will do is I will take inverse Laplace transform. So, when I do inverse Laplace transform, z of s becomes z, and so it will be okay. I will just first multiply it, s power n times z of s plus a1 s power n minus 1 times z of s plus so on to a n z of s is equals to u of s. Now, when we apply Laplace inverse, s power n becomes nth derivative of z. So, I can write it as z n in the brackets. So, this is a notation to denote that we are taking the derivative of z n times, and so we will just follow the same thing, a1 z power n minus n minus 1 derivative of z and so on up to a n z is equals to u. So, when we take the Laplace inverse, we are representing everything in small letters. So, z of s becomes small z and u of s becomes small u. Now, on this differential equation, we will be defining our state variables. So, here is how we define. So, I will define my x1, I need to define n state variables. So, x1 I will take it as z, and x2 I will take it as x1 dot which will be equal to z dot. So, that is the first derivative of z, and then x3 will be x2 dot which will be equal to z double dot, and I will go on up till x n is equals to x n minus 1 dot which will be equals to n minus 1th derivative of z, and x n I will write here x n dot is equals to the nth derivative of z. So, this nth derivative of z I will take it from here, I will take all these terms and send them to the other side and write it here. So, that will be u minus a1 n minus 1 the derivative of z minus so on up to A n z. Now, you can see that we have n minus 1 derivative of z, n minus 2 derivative of z, so on up to z, and all these variables are already defined in terms of the state variables. So, we will just substitute them here, and my x n dot can be written as u minus a 1 times x n minus a 2 times x n minus 1, so on a n times x 1. So, now you can see that we have represented all the state variables in terms of x's. Now, so now we have a set of equations. So, what are those equations? The first one is x 1 dot is x 2, x 2 dot is x 3, so on x n minus 1 dot is x n, and x n dot is this expression. So, using all these equations we can write the state space model. So, the state space model will be x dot, which is nothing but x 1 dot, x 2 dot, so on up to x n dot is equals to. So, what is x 1 dot? It is simply x 2. So, I can write it 0 1. Okay, I will just have to get a matrix here times x 1 x 2 so on up to x n. Now, you can see that this will be 0, this will be 1, and rest all again will be zeros, because x 1 dot is just x 2. Now, x 2 dot is just x 3. So, I will get a 1 here, and rest all will be zeros. And similarly, finally, x n dot will be a n minus a n times x 1. So, here it will be minus a n minus a n minus 1 and so on up to minus a 1 plus. So, none of these first n minus 1 state variables have input. So, this will be all zeros except at the end times u. Now, if you simply multiply these matrices and observe, you will get those set of equations exactly same. Okay. So, this is what we call the controllable canonical form. So, and this will be A, this will be B, and you can see output y. So, okay, to get the output y we have to use the other set of equations. So, I can take this and say y of s is b 1 s n minus 1 times z of s plus so on b n z of s. So, here again I can take the Laplace inverse and just use those equations, then my y of s will simply be when we take the Laplace inverse, it will be just y, or y of t is equals to b 1 times so this will be n minus 1 derivative of z, which is x n plus b 2 times x n minus 1 plus so on b n x 1. So, this will be the equation for y of t, and in the matrix form I can just write it as b n, okay, this is n b n. So, in the matrix form I can write it as b n minus 1 so on up to b 1 times x. So, x is the state vector. So, this matrix will become my output matrix C. So, now you have A, B, C and D is equals to 0. So, when we use these matrices, the state space model that we get is the controllable canonical form. So, why is it called the controllable canonical form? I will draw a small diagram and you will be able to see. So, we will draw a small block diagram to represent this. So, I will start with state x1 and so here I put an integrator block. So, this will be x1 dot, because when I integrate x1 dot I will get x1 and this x1 dot is nothing but x2. So, similarly I can put a series of integrator blocks and get up to xn, and then I add another integrator block to get xn dot, and to get the value of xn dot. So, as you can see, xn dot is summing up or over all the state variables with certain coefficients. So, we need to put a summer here and with the input, because it is u plus all this. So, u plus minus a1 times xn. So, my xn is here, I can just take a feedback from here and put minus a1, and similarly it will be another feedback from x2 which will have a coefficient minus an minus 1, and similarly from x1 we will have another feedback with a coefficient minus an. So, just forgetting the output for a while, we can see that the input u is passing through all the state variables xn, xn minus 1, xn minus 2, so on up to x2 and x1. So, output y will actually come out here somewhere. So, it can be observed that input has a control over all the states in the system, which is clearly observed to this block diagram, and that can be clearly seen in this matrix. So, this is the reason why we call the controllable canonical form, because the input has control over all existing states, and that can be clearly seen. So, if you want the output, you can further extend the block diagram by adding bn here, and so output y sums over bn times xn x1, and so it will be bn minus 1 times x2 and so on up to b1 times xn. So, that is the complete block diagram of the state space model, and you can clearly see why it is a controllable canonical form. So, now we look at the observable canonical form. Okay, now coming to the observable canonical form. This actually becomes very simple once you know the controllable canonical form. So, once say A, B, C and D are the matrices pertaining to the controllable canonical form. So, the matrices pertaining to the observable canonical form can be written as follows. I will call them as A bar, B bar, C bar and D bar. So, A bar is nothing but A transpose, B bar is nothing but C transpose, C bar is nothing but B transpose and D bar is nothing but D transpose. So, this will be the observable canonical form. So, you can just find out the controllable canonical form and take the transforms of those matrices and arrange them in this manner to get the observable canonical form. Okay. So, now we will look at the diagonal canonical form. So, again we will start with the strictly perfect transfer function. So, what we will do is we will take this denominator and factorize them, factorize the n roots by writing it in this form. So, P1, P2, P3 so on up to Pn are the roots of the denominator polynomial, and so we can write it where we can write the denominator in this form s plus P1 times s plus P2 times so on up to s plus Pn. Now, what we will do is we will apply partial fractions, and I can write it in this form C1 by s plus P1 plus C2 by s plus P2 plus so on Cn by s plus Pn. Now, what we will do is we will send u of s to the other side and say u of s C1 by s plus P1 plus u of s C2 by s plus P2 plus so on u of s Cn by s plus Pn. Okay. So, now I will define each of these parts, leaving the c's. I will define that as x1 of s. So, x1 of s is equals to u of s by s plus P1. So, I will cross multiply and now I take the inverse Laplace. So, when we take the inverse Laplace of s times x1, it will be just x1. So, earlier also and here also when we took the inverse Laplace, we assumed that all the initial conditions are 0. So, you should remember that when we apply this inverse Laplace, we are assuming that all the initial conditions are 0. So, s times x1 of s, when take in the inverse, it becomes just x1 dot plus P1 times x1 is equals to u. So, these are all again time based variables. So, I can just write x1 dot is equals to u minus P1 x1. So, similarly, I will take each of these as x2 of s, x3 of s so on up to xn of s, and just repeat the same process, and I will get x2 dot is u1 minus P2 x2 so on xn dot is u minus Pn xn. So, now I have all the state variables and their derivatives. Now, I can write the canonical form. I will just write the matrices directly. So, A will be P1, P2 so on Pn along the diagonal, and all the terms will be zeros. So, this is a diagonal matrix. So, that is the reason why we have the name diagonal canonical form. And then B will be all ones, because in every x1 dot, x2 dot, so on xn dot we have a u. So, it will be all just ones times, okay, u will not come here, just B, and C will be, so you can see y is x1 times C1 and plus x2 times C2 plus so on up to xn times Cn. So, C will be just C1, C2, so on up to Cn, and D will be anyway 0. So, these are the matrices pertaining to the diagonal canonical form. So, now we will try to look at an example. So, we will just solve one example and try to derive all the three forms. So, the transfer function is g of s is equals to 1 by s cube plus 6 s square plus 11 s plus 6. Okay, so, this is the transfer function that we take, and so when we are deriving the canonical forms, there are two ways of going at it. One way is actually deriving all the state variables, and other way is remembering what we got, the matrices A, B, C, D, and this trying to substitute the coefficients of these polynomials into them. So, you can do it either way, but if you try to remember the formula, it might become bit complicated, because you need to know which coefficient pertains to which of those, because even in the textbooks some people use it in a different way. Some people use it from B naught to Bn, and some people do it from Bn to B naught, and also in the denominator people also use it in the reverse. So, when you remember the formulas, it might become a bit difficult. So, what I will do is I will try to derive the state variables using the way that we did earlier. So, I will just take y of s. So, this I will take it as y of s times u of s, and so I can write y of s times s cube plus 6 s square plus 11 s plus 6 is equals to u of s. So, I just did cross multiplication. Now, I will apply Laplace inverse assuming 0 initial condition. So, it will be y triple dot plus 6 y double dot plus 11 y dot plus 6 y is equals to u. So, now I got the differential equation. Now, I can define my state variables. I will define x1 is y, x1 dot is is x2, which will be y dot, x2 dot will be x3, which is equals to y double dot, and x3 dot will be just y triple dot. So, we just have 3 state variables x1, x2 and x3. Now, we can substitute them here. So, actually we already know x1 dot and x2 dot, and x3 dot is y triple dot, which I will find out from this equation. Get it as u minus 6 y double dot minus 11 y dot minus 6 y, and again y double dot, y dot and y I can substitute it from these. So, I will get u minus 6 x2 minus 11 u minus 6 x3 minus 11 x2 minus 6 x1. So, now I have the values of x1 dot, x2 dot and x3 dot. Now, you can simply write the model as x is equals to 0 1 0 0 0 1 minus 6 minus 11 minus 6 times x plus 0 0 1 times u, and y is just x1 in this case. So, it will be just 1 0 0 times x. So, this is the controllable canonical form. As you can see, it is very easy if you can derive it out directly instead of remembering the formulas. So, now we have the controllable canonical form. So, I will say I will call this okay, this is the controllable form. So, what about the observable form? Observable form will be simply x is equals to, so as A is equals to A transpose, I just had to take the transpose of this. So, it will be 0 0 minus 6, 1 0 minus 11, 0 1 minus 6 times x plus B is just C transpose. So, that will be 1 0 0 times u, and C will be B transpose. So, it will be 0 0 1 times x. So, this is the observable form. So, finally, the diagonal form. So, to get the diagonal form, we need to find the roots of the denominator polynomial. So, I am just I already found them to be minus 1, minus 2 and minus 3, you can verify. So, I can write my y of s by u of s as 1 by s plus 1, s plus 2, s plus 3, and this when I apply partial fractions, I will get 1 by 2 by s plus 1 plus minus 1 by s plus 2 plus 1 by 2 by s plus 3. So, this also you can verify yourselves. And so, now we have this partial fractions. My A is nothing but these 3 coefficients, sorry, these 3 roots coming in the across the denominator. So, it will be minus 1, minus 2, minus 3, and rest all will be zeros, and then B is all just ones, and C is the numerators of the partial fraction. So, it is half, minus 1 and half. So, this is the diagonal canonical form. So, we just took one example and we tried to derive all the 3 canonical forms. So, there might be some special cases where you might not be able to derive the diagonal form, because there can be repeated roots and not unique roots as in this case. So, that is when you go to something called a Jordan canonical form, which we are not doing as of now. So, these are the canonical forms which we discussed. So, I will try to put up some more problems which you can try out as an exercise. S plus 3 times s square plus 3s plus 2 and s square plus 3s plus 3 by s square plus 2s plus 1. So, you can just try out these 2 examples and you can see that this last example actually has a non-zero d. So, you need to perform polynomial division first and then apply whatever we did until now. So, you can just try out those and maybe we will try to give them as assignment problems. Thank you.